And so that leads, the total effect that this has on our revenue then, right, is it increases it by 1 minus 10 to the 6th, right? But then it decreases it by this term here, right? So that's the total effect it has on our revenue. And so the optimal tax rate is going to equate this on average to 0, right? So averaged over all the people hit by this tax, this thing should be 0. Because this is the contribution to our revenue made by each person. Okay. And Saez 2001 develops a very simple formula for dealing with this. So he says, if we average over the population, this should become the average income of people earning over $1 million. And this should become the income-weighted average elasticity of people earning over. So that here's a different average elasticity. Rather than E bar, this is E bar sub 10 to the 6th, which is the average elasticity weighted by income of people earning over $1 million. Right? And so we get this formula, and now let's define alpha to be the average value of people, the average income of people earning over $1 million divided by that average income minus $1 million. Right? So that's like, it's the amount that they earn, the average amount they earn over $1 million divided by the total amount that they earn on average. Okay, and using the exact same logic from above, Abigail, what formula do we get for the optimal tax? You can come do it on the board if you want, or...
I don't think I can answer that.
What?
I don't think I can answer that.
Well, so here's the thing. You just have to set that equal to 0, right? You just have to solve out for 10 to the 6th. T sub 10 to the 6th that sets this equal to 0. It's just a little bit of algebra. You can do it. Okay. Does anyone else want to say what we got or try to work it out? Yeah, go ahead, Cody.
I'll say what we got. We got
Well, why don't you come do it on the board? All right. This should not be that hard. That should be I, right? Not T.
I bar?
Yeah, that's I bar out there, right?
Yes.
Okay. Yeah. Oh, I see. You didn't put the top. Yeah, great.
Better?
That would be great.
Professor?
Yeah.
So I have a really, really stupid question,
Yeah.
but why are we setting the average revenue equal to 0?
No, this is the average marginal revenue.
Average marginal, okay, sorry.
Right, so this is just a monopoly problem. This is exactly a monopoly problem where you can, set a different rate for people purchasing above a certain amount, right? Yeah, you actually, just because it'll make your life easier, if you bring this over and subtract it there before you divide by 10 to the 6th by I bar, it's going to make your life easier.
Say that one more time.
If you move this guy, move this over there before you divide through by I bar 10 to the 6th, like you did
So
there,
this term needs to be over here.
or you can just move this one over here.
Okay.
That'll be fine.
Is that good?
Well, then this would have to be negative then, because you just erased the negative on this. Yeah. Yeah. to put a parentheses around the 1 minus t. Right? Yeah, so you've got to get all the terms that involve t onto one side before you can divide through.
Oh, well.
Otherwise, it's going to be a mess. But one thing that will simplify your life a lot is that if you put through that 1, that'll be 10 I bar 10 to the 6th minus 10 to the 6th over I bar. And so this whole thing is just 1 over epsilon, alpha, as we defined alpha.
Okay.
Right? Let me do it.
You said that term is equal to what?
This term is 1 over alpha. Right? So this
Start
is
over.
epsilon, yeah, start with that.
And we're solving for
T.
Okay, so I'm going to move this over here. And that over
We need to get all the t terms on the same side, right? And then factor out the t out of them.
Okay.
So you've got the epsilon bar and
So move
the,
an epsilon over here, and then this over here.
you've got to get this 1 separated from the t bar apart. You see what I mean? Yeah.
There you go,
Okay.
sorry.
Let me do it. Okay. So so you've got this, right? You take this term, part of the term. So and then you have a 1 over alpha over here, and you bring over t 10 to the 6th times epsilon bar 10 to the 6th plus 1 over alpha. Divide that through and you get that. So 1 over alpha over 1 over alpha plus epsilon bar 10 to the 6th. This is like super similar to our other formula, right? It's exactly the same, except that our measurement of inequality is now 1 over alpha rather than sigma bar. And sigma bar is basically the same thing as the Gini coefficient, and 1 over alpha is basically the same thing as the top income shares. So what this says is there's these two different notions of inequality that apply to these two different things. The average income tax we should charge is based on the average inequality. This is based on the top income share. So again, we have the equity efficiency trade-off, and we say taxes are progressive if the amount that we charge to the rich is greater than the average rate that we charge. So that is, taxes should be progressive if the top income share is greater than the Gini, basically. And taxes should be regressive if the reverse happens. Also, taxes should be progressive if the rich have a lower elasticity of labor supply than most Americans, and should be regressive if they have a higher elasticity of labor supply than most Americans. Right? Okay. So now I want to try to get a sense for alpha and sigma. So one useful way to do this is to think of the income distribution as being broken into 2 parts. So there's what most people earn, and that's going to be given by a log logistic distribution, which is very similar to a log normal distribution that you use. And the nice thing about a log logistic distribution is that the beta parameter, which measures its variance, is just 1 over the Gini. And the Gini in the United States is 0.45. Its mean is given by this expression. Again, these are things you can pull off the internet. Given that mean income in the US is about 46,000, we can calculate that alpha has to be 32,168. And if we throw this into Mathematica, we can just graph what our inequality measure was as a function of the tax rate. Right? As the tax rate increases, people get pushed towards the middle of the distribution, and this inequality goes down. Okay. And so then we can just plug this into our nice formula from back here, right? And we get the optimal income tax rates. So here's the tax rate, and here's that sigma over epsilon times 1 plus sigma, epsilon plus sigma, graphed for different values of the epsilon bar, different values of the elasticity, and the intersection represents the optimal tax rate, right?
What's on the x-axis and what's on the y?
X-axis is the tax, and this is the tax as well. So the point is that this is sort of like what the optimal tax would be, and this is what the tax rate actually is, and so when they're equal to one another, that's the optimal, right? Okay, so when the elasticity is 0.1, the optimal tax rate would be about 70%. When the elasticity is 0.3, it's about 50%. When it's about 0.5, it's about 39%, which is like not too far off from what we have. Probably what we have is a little bit closer to 1. So the average tax rate that people pay is about 25% of their income, right? So if the elasticity of labor supply was 1, that would about justify the system that we currently have. Yeah, Edward.
So wait, I'm sorry, like what was the y-axis again?
Okay,
The
so
x-axis?
this was, what I'm graphing here is our formula, this right-hand side of the formula, as a function of the tax rate, right? And so the optimum is at the intersection between the right-hand side and the left-hand side, right? The left-hand side was just the tax rate, this is the tax rate, and this is the optimal tax rate as a function of the tax rate, right? Because as we increase taxes, the inequality goes down, and so we want to tax less, right? And so the optimum is at the intersection of these two things. Yeah, sure.
Could you also explain how sigma is conceptually dependent on elasticity?
It's not. But the formula is because the elasticity is down in the bottom. So if we just change that number that's down in the bottom, that's going to change the height of these graphs, right? As we increase the elasticity, right, that's going to make the right-hand side lower, right? Okay. So calculating alpha is actually even easier because we know that the top part of the U.S. income distribution is a Pareto distribution with coefficient 1.5, and we can just calculate that the average income of people earning over $1 million is going to be the average value under a Pareto distribution of the income over the integral of the Pareto distribution above $1 million, and just factoring things out, we can take these out and we just get I to the negative alpha from 1 million to infinity over I to the negative alpha minus 1, and that's just the most basic integral. You divide by 1 over 1 plus that thing, right? And you get these evaluated from 1 million to infinity, and at infinity, anything with this negative power is going to be 0, right? So you just get minus this thing to 10 to the 6th, and that comes out to be exactly 10 to the 6th times alpha over 1 minus alpha, where alpha is, rather than being the alpha we talked about before, is the Pareto coefficient, is the Pareto parameter alpha. But if we then calculate what is I bar 10 to the 6th over I bar 10 to the 6th minus 10 to the 6th, it's alpha over alpha minus 1 over alpha minus 1 minus 1,